The evaluation of the universe's commencement and its constant development is at a critical stage. At the moment, some aspects of cosmology face essential uncertainties. A vital focus is on what determines how quickly the universe has been expanding. For more than a century, two significant approaches to measuring this growth have resulted in conflicting results. Recent observations of the current state of the universe demonstrate that the expansion rate, known as the Hubble constant, is around 9% higher than predictions derived from early universe data. Scientists had hoped that the James Webb Space Telescope, the most advanced telescope ever made, would offer a definitive solution to this problem. However, the groundbreaking new data from JWST has only deepened the discrepancy, leading to questions about the validity of the well-established model of the universe. This has sparked intense debates within the academic community regarding whether physics needs to be adjusted or whether current theories, held for over 4 decades, should be completely replaced. This possibility is both exciting and unsettling because it suggests that we might be ignoring an essential aspect of the universe that has the potential to drastically alter our understanding of its origins. The beginnings of the universe. Tracing back to the Big Bang, an instant explosion produced energy, matter, and space. The universe began as an intensely hot and dense plasma, a mixture of matter and antimatter particles. These particles collided and annihilated one another. However, scientists think a subtle imbalance permitted a slight increase in matter over antimatter, preventing the universe from destroying itself. The plasma was then compressed by gravity, heating it to the point where sound waves, known as baryon acoustic oscillations, propagated through it at speeds greater than half the speed of light. As the high-energy density of space-time grew, the universe expanded. Eventually, normal matter began to gather around invisible dark matter, leading to the formation of the first galaxies. The role of dark energy. These initial galaxies are believed to be interconnected by a vast cosmic web, linked through dark matter and energy. As the universe continued to expand, both the energy density and the rate of expansion gradually decreased. However, around 5 billion years ago, galaxies began moving away from each other at an accelerated speed, driven by a mysterious force referred to as dark energy. The most widely accepted theory about dark energy suggests that it is a continuous force woven into space-time itself. According to Einstein's general relativity, this force, represented by lambda in a lambda CDM model, lambda cold dark matter, maintains a steady density as the universe grows, while the density of normal matter declines. Over billions of years, dark energy has taken over as the primary driving force of the universe's expansion. The Hubble tension, a major cosmological challenge. One of the most significant challenges facing cosmologists is the Hubble tension, an inconsistency in measurements of the universe's rate of expansion depending on the method used. Different measurements yield conflicting results, making this discrepancy one of the most critical issues in the field. Observations from the early universe suggest a slower expansion rate than the lambda CDM model predicts. These early measurements have been rigorously tested and validated through various observations made by Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest JWST measurements. The only possible explanation for this inconsistent behavior is that our existing model lacks something crucial. Measuring the universe's expansion rate requires more than merely making observations. One of the primary methods is analyzing the cosmic microwave background, CMB. The universe's first light emitted approximately 380,000 years after the Big Bang. Between 2009 and 2013, the European Space Agency's Planck satellite produced a comprehensive map of the CMB, showing a nearly uniform universe with slight temperature variations. These variations mark regions of higher and lower matter densities and reflect the imprint left by baryon acoustic oscillations. Using this data, cosmologists calculated the Hubble constant at approximately 67 kilometers per second per megaparsec, MPC. This means that a galaxy 1 MPC away would recede at 67 kilometers per second, while a galaxy 20 mpc away would recede at 1,340 kilometers per second. If a galaxy were farther than 4,175 mpc, it would recede faster than the speed of light. Alternative methods for measuring the expansion rate. Another method for determining the expansion rate involves studying Cepheid variable stars, stars with pulsating outer layers that expand and contract in a regular pattern as they absorb and release radiation. Discovered by astronomer Henrietta Swan Leavitt in 1912, this behavior allowed researchers to determine a star's absolute brightness and estimate its distance. The Cepheid variable method, a key part of the cosmic distance ladder, has been essential for measuring vast distances across the universe. By measuring Cepheids in the Milky Way and other nearby galaxies, astronomers can determine the distances of more distant galaxies and analyze their redshifts to calculate the Hubble constant. In 2019, Adam Rees and his team used this method to study the Large Magellanic Cloud, the Milky Way's closest neighbor. Their results were surprising, showing a significantly higher expansion rate of 74 kilometers per second per mpc compared to the Planck data. While the Hubble Space Telescope, HST, contributed significantly to these measurements, its accuracy was limited in congested regions of space, where distant Cepheids appeared obscured by nearby stars. Some astronomers suggested that the discrepancy might be due to measurement errors. However, when the James Webb Space Telescope, JWST, launched in December 2021, expectations were high that it could either resolve or confirm the inconsistency. JWST's findings and the need for new physics. With its 6.5-meter wide mirror, nearly 3 times the size of Hubble's, JWST possesses superior infrared capabilities, allowing it to observe fainter objects and detect a broader range of wavelengths. Studies comparing Cepheids in NGC 4258 with supernovae revealed results nearly identical to Rees's previous findings, confirming an expansion rate of about 73 kilometers per second per mpc. Other measurements, including those by Wendy Friedman using Hubble and gravitational lensing techniques, returned similar values, 69.6 kilometers per second and 66.6 kilometers per second per mpc, respectively. These findings have caused a stir in the cosmological community. Cosmologist Ronan Keene from the University of California argues that even a small inconsistency of 7 kilometers per second is highly unlikely to be a random error, given the precision of these measurements. This has led to a division among cosmologists, some attributing the discrepancy to measurement errors, while others argue that new physics is needed. One of the most prevalent theories is that dark energy's behavior may have changed over time. If dark energy was once stronger and has gradually weakened, it could have made the early universe appear smaller, leading to a faster expansion rate. Other theories propose the existence of 2 types of dark energy or interactions between dark matter and light, though these ideas remain speculative. The future of cosmology. JWST's discoveries are reshaping our understanding of dark energy, dark matter, and galaxy formation. Observations of early galaxies formed just. The Hubble tension remains one of the most perplexing challenges in modern cosmology. If the lambda-CDM model is incomplete, physicists may need to introduce new fundamental physics to resolve the discrepancy. Several theories have been proposed to explain the difference in expansion rate measurements. 1. New physics beyond lambda-CDM. Some researchers propose that the cosmological constant, lambda, which represents dark energy in Einstein's equations, may not actually be constant. Instead, dark energy could be evolving over time, affecting how expansion rates appear at different cosmic epochs. Others suggest that dark matter could interact with normal matter or radiation in previously unknown ways, altering early universe dynamics and leading to systematic shifts in expansion measurements. 2. Systematic measurement errors. Some astronomers argue that unresolved observational biases might still be influencing results. For instance, differences in how Cepheid variable stars and type Ia supernovae are calibrated in different telescopes could introduce small but significant inconsistencies. while JWST's superior infrared capabilities have helped refine these measurements. Further cross-checking with future observatories is needed. 3. New observational approaches. The Roman Space Telescope, Nancy Grace Roman Space Telescope, set to launch in the 2030s, will further investigate dark energy and cosmic expansion using an independent method called weak gravitational lensing, measuring the distortion of light from distant galaxies due to intervening mass. The Euclid Space Telescope, launched by the European Space Agency, is also designed to map the large-scale structure of the universe, offering more insight into cosmic expansion beyond the Hubble tension, expanding the frontiers of cosmology. While much of the focus remains on dark energy and dark matter, JWST is simultaneously transforming our understanding of galaxy formation, black holes, and, as JWST continues to gather information, it becomes increasingly clear that we are on the verge of discovering new physics. Whether unraveling the nature of dark energy, exploring the unexpected early complexity of galaxies, or examining the behavior of dark matter, JWST is opening new avenues for understanding the universe. The telescope is not limited to improving existing theories. It is challenging them, encouraging scientists to reconsider fundamental assumptions and explore new possibilities. These findings push the boundaries of physics, astronomy, and even philosophy as we improve our comprehension of the laws that govern our existence. As we continue to investigate the cosmos from a JWST point of view, we're not just gaining knowledge of distant stars and galaxies. We're gaining profound perspectives on the very nature of the cosmos. The questions raised by JWST discoveries could lead to a paradigm shift in how we understand the origin, structure, and future of the universe. As we keep looking into the universe through the lens of the James Webb Space Telescope, the potential for a paradigm shift in our understanding of the universe becomes increasingly possible. The telescope's extraordinary capabilities have already provided a wealth of information that challenges many of our long-held beliefs regarding the universe. For example, the discovery of the first massive galaxies forming only 300 million years after the Big Bang raises significant questions about galaxy formation. These galaxies appear far more developed than anticipated, indicating that certain processes, like the formation of stars and black hole growth, may have occurred much more quickly and effectively than previously believed. This discovery has sparked intense discussions within the scientific community about whether our current models of cosmic structure and galaxy evolution need to be revised. Additionally, JWST's exploration of the early universe has revealed further complexities in the interactions between matter, dark energy, and dark matter. The telescope's infrared capabilities allow it to observe objects and events that occurred in the first few hundred million years after the Big Bang, a period that was previously beyond our observational reach. These observations are crucial for understanding the role of dark matter, which makes up about 25% of the universe's mass, but remains one of the most mysterious components of the cosmos. While dark matter does not emit light and can only be detected through its gravitational effects, JWST's precision may help clarify how dark matter played a role in the formation of galaxies and large-scale cosmic structures. This is a crucial step toward understanding how our universe took shape and how it continues to evolve. In addition to the ongoing quest to understand fundamental components of the universe, such as dark matter, dark energy, and galaxy formation, JWST's observations are also opening exciting new possibilities in the search for life beyond Earth. One of the telescope's primary goals is to investigate the atmospheres of exoplanets, searching for signs of habitability by analyzing their chemical composition. Scientists hope to determine whether molecules such as oxygen, methane, and carbon dioxide, potential indicators of life, are present in these atmospheres. JWST's ability to observe exoplanets with higher sensitivity and greater detail could bring us closer than ever before to answering the profound question, are we alone in the universe? JWST's contributions to this field go beyond simply identifying potentially habitable areas. It also helps us understand the environmental conditions of exoplanets that could support life. This includes studying atmospheric composition, climate states, and how these factors influence the potential for life to emerge. By examining the chemical interactions within exoplanetary atmospheres, researchers hope to gain new insights into the processes that govern planetary habitability, insights that could have profound implications for the search for life beyond Earth. JWST's unprecedented capabilities are not just refining our understanding of existing models. They're also challenging fundamental beliefs regarding the universe's formation, structure, and evolution. As more data is collected, scientists are making observations that do not always correspond to our current theories, suggesting that new physics may be required to explain these anomalies. One of the most surprising revelations is the discovery of massive galaxies forming much earlier than expected. Previously, it was believed that galaxy formation was a slow process, requiring hundreds of millions of years for galaxies to gather sufficient mass and structure. However, JWST has revealed galactic systems that appear mature and well-developed only a few hundred million years after the Big Bang. This raises important questions about the efficiency of initial galaxy formation and suggests that either our understanding of how matter clumped together in the early universe is incomplete or that certain processes, like star formation and black hole growth, occurred much faster than previously believed. Another significant area of study that JWST is advancing is the nature of dark matter. While its presence is inferred from its gravitational effects, its true nature remains unknown. JWST's ability to observe the early universe with high precision may provide insights into how dark matter influenced the formation of cosmic structures. By studying the locations of galaxies and their interactions with dark matter over time, scientists hope to uncover clues about its properties and behavior. Some theories suggest that dark matter may be composed of exotic particles, while others propose modifications to gravity itself. JWST's observations may help distinguish between these competing theories. Similarly, JWST is shedding new light on dark energy, the mysterious force driving the universe's rapid expansion. One of the most puzzling aspects of dark energy is the Hubble tension, a disparity between different measurements of the universe's expansion rate. JWST's ability to observe distant supernovae and galaxies with incredible precision could help resolve this tension by providing new, independent measurements of cosmic expansion. Some alternative theories suggest that dark energy may evolve over time or interact with matter in ways not yet understood. If JWST detects variations in dark energy's behavior throughout the cosmos, it could fundamentally change our understanding of the fate of the universe. Beyond these fundamental physics questions, JWST is revolutionizing the study of exoplanets. Using its powerful infrared capabilities, JWST can analyze the atmospheres of distant planets, searching for evidence of life or conditions that could support habitability. The telescope has already detected key molecules such as carbon dioxide and methane in exoplanet atmospheres. These findings provide crucial insights into the diversity of planetary environments outside our solar system. One of JWST's most exciting objectives is to identify potential biomarkers, chemical signs of life, in exoplanet atmospheres. By detecting gases such as oxygen, ozone, and methane in proportions suggestive of biological activity, scientists might discover the first hints of extraterrestrial life. While detecting life beyond Earth is an enormous challenge, JWST represents a major step forward in this quest. Future observations will focus on planets within the habitable zones of their stars,